Hello everyone. So in this one shot I'm going to discuss thermodynamics. So we're going to see 20 problem types that can be asked from this chapter, and it's going to be a revision video, so I'm not going to derive any formula. We'll discuss all possible concepts that can be asked. Now this is the syllabus for thermodynamics in JEE 2025. So first there is thermal equilibrium, which is basically the zeroth law of thermodynamics. Then the concept of temperature, zeroth law of thermodynamics, and then heat, work, internal energy. Then first law is there, isothermal and adiabatic processes, but we'll also see isobaric and isochoric processes, and cyclic and the polytropic process. And then the second law of thermodynamics, like reversible and irreversible processes. Now let us see different concepts and problem types that can be formed from this chapter. So in zeroth law of thermodynamics, let us say we have three thermodynamic systems A, B and C, and they are at a different temperature initially. Now we have covered these three systems with a adiabatic wall, which is nothing but a perfect insulator. Now we have connected A and C with a diathermic wall and B and C with a diathermic wall. And what is a diathermic wall? It is a perfect conductor. Now, due to this diathermic wall, the heat will flow from high temperature to low temperature, and after some time, A and C will attain a thermal equilibrium, which means both will have the same temperature, and B and C will attain thermal equilibrium, and both will have the same temperature. Now, according to this law, if A and C are in thermal equilibrium and B and C are in thermal equilibrium, then we can say A and B are in thermal equilibrium. So that is all about first zeroth law of thermodynamics. Now let us see work done by a gas. Now this is a very important topic. So you will definitely get a question where you have to calculate work done. So suppose there is a cylinder which contains some gas and there is a piston. And due to the pressure of the gas, there is a displacement in the piston. And let us say the displacement is dx. So this displacement is dx, and the area of cross section of the piston is A. So we can say the increase in volume will be dV, which will be area of cross section times the displacement. Now the small amount of work done by the gas will be given by F times the displacement dx. And what is this F? So F is the pressure of the gas times the area of cross section times dx, right? So this is basically the work done, P A dx. Now A dx is nothing but the change in volume, or you can say the increase in volume. So this will become P dV. So we can say the small amount of work done by the gas will be P dV. Suppose the volume is changing from V1 to V2, right? So let us say we have a P on the y-axis and V on the x-axis, and the volume is increasing from V1 to V2. So if I want to find the work done, if I integrate this equation, I will get the work done for that particular expansion or compression. So this area will give us the work done by the gas. So if there is expansion, work done will be positive. If there is compression, work done by the gas will be negative. So we can say the work done will be given by this formula. This is the general formula. We can apply this for any process. So integral P dV, where V is varying from V1 to V2. And it is also, if the graph is given to you, you can find the area under pressure volume graph, and you will get the work done. Now for different processes, in isochoric process where volume is constant, work done is 0. And in case of an isobaric process, the work done will be given by P delta V, where delta V is the change in volume, and NR delta, so we can, by using ideal gas equation, it can be written as NR delta T. So you should remember all these formulas. And in case of an isothermal process, when the temperature is constant, it is the nRT ln V2 by V1, where V2 is the final volume, V1 is the initial volume. And for isothermal process, P1 V1 is equals to P2 V2. So we can write V2 by V1 as P1 by P2. So again, very important formula. Now in case of an adiabatic process, it's a process where there is no heat exchange with the surrounding. The work done will be given by negative of P2 V2 minus P1 V1 upon gamma minus 1. We'll see what is gamma, right? When we have already studied this in kinetic theory of gases. So gamma is nothing but the ratio of molar heat capacity at constant pressure and volume. So P2 V2 minus P1 V1 can be written as NR delta T. So again, you should remember this. Then we have a polytropic process. In polytropic process, gamma will be replaced with A, which is not a molar heat, which is not the ratio of molar heat capacity at constant pressure and volume. So just replace gamma with A. So it will be minus P2 V2 minus P1 V1 upon A minus 1, which can be written as minus NR delta T upon A minus 1. And for a cyclic process, if we have given a cyclic process, the work done will be given by the area enclosed. Can you see this shaded area? The yellow area, this is the work done. in the cyclic process. If we have a counterclockwise cycle, the work done will be negative. If we have a clockwise cycle, the work done will be positive. Now let us see this illustration based on work done by a gas. So here we have given the pressure and the volume of the ideal gas is given by PV raised to power 3 by 2 is constant, and the work done by the gas when the gas is taken from the state A to state B, and this at state A pressure is P1, volume is V1, temperature is T1, and similarly for state B it is P2, V2 and T2. So okay, right, so now let us try to solve this. Here we have given PV raised to power 3 by 2, which is constant. And we know that in case of a adiabatic process, we have the similar form, right, which is PV raised to power gamma, which is constant. And in this particular case, in adiabatic process or in polytropic process, work done is defined as, it will be P1 V1 minus P2 V2 divided by gamma minus 1 in case of adiabatic process, or in polytropic it will be n minus 1. So here we have 3 by 2, so we can write this as 3 by 2 minus 1. So this comes out to be 2 times P1 V1 minus P2 V2. Now if you look at the options, P1 V1 minus P2 V2, so option 1 is the right answer. A thermodynamic system is taken from the state A to state B by a linear process as shown in the figure. So this is the linear process they are talking about. Its volume is then reduced to the original volume from B to C by a isobaric process. So this process is isobaric, constant pressure, and the total work done by the gas from A to B and then from B to C would be, right, so we have to find the work done, sum of the work done from A to B and B to C. So W from A to B plus work done from B to C. Right, so from A to B, we know that the work done will be given as the area under the graph, pressure volume graph. So if let me show this with red color. So the area under AB graph will be this, right? This trapezium. So what is the area of this trapezium? Let us find the sum of the parallel side. So the parallel sides, this will be 800 dynes per centimeter square. This will be 4,000 dynes per centimeter square. 8,000 and 4,000. So we can say work done from A to B can be written as half sum of parallel sides, that will be 12,000 dynes per centimeter square. This can be written as 10 raised to power minus 5 divided by 10 raised to power minus 4. Now we have converted pressure in SI units. Now let us multiply this with the distance between the parallel side, which is nothing but 7 minus 3, which is 4, and it is in meter cube. Right, so we got the work done from A to B in joules. Now let us find the work done from B to C. And as you can see, from A to B there is an expansion, so it will be a positive work done. But from B to C there is a compression, so it should be a negative work done. So let me put a negative sign here. And then the pressure is 4,000 dyne per centimeter square, so that can be written as 10 raised to power minus 5 divided by 10 raised to power minus 4 pascals, and multiply this with the change in volume, and volume is decreasing, so this will be 4, right? Now let us simplify this. So this comes out to be 2 times 1200 plus, and this will be negative, it will be 1600. So 2400 minus 1600, so that will be 800 joules, right? So option 4 is the right answer, right? So now let us see the next question based on the same concept. A total of 48 joules heat is given to 1 mole of a helium gas kept in a cylinder. The temperature of the helium gas increases by 2 degrees Celsius. So that is the change in the temperature. What is the work done by the gas? So it's a so volume is constant, 1 mole of gas is given, heat is also given, right? So delta Q is given as 48 joules, and the temperature is increased, so delta T is also given, which is 2 degrees Celsius, and we have given N as 1, and it's a helium gas, and we have to find the work done, right? So now let us see what is the change in internal energy of the gas, and this is given as F by 2 nR delta T. So it is a monatomic gas. In case of a monatomic gas, the degree of freedom is 3, 3 by 2, and the number of mole is given as 1. R is given as 8.3, and the increase in temperature is given as 2. So this comes out to be 24.9 joules. Now we got the change in internal energy. We know what is the heat supply to the gas. Now we can apply first law of thermodynamics. That will be delta Q will be delta U plus delta W. So the work done will be given as the difference of the heat supplied and the change in the internal energy. So it will be 48 minus 24.9, which comes out to be 23.1 joules. So option 4 is the right answer. Now here we have given a cyclic process. Now we have to find the work done. So can you see this cyclic process? So we have a triangle. So basically we have to calculate the area of this triangle. So it will be half base. Base will be 4 minus 2. And the height will be 400 minus 100. So this will become 300, right? 300 joules. So that is the work done by the gas, and it is a clockwise cycle, so it will be a positive work done. So the answer is option 2. Now let us see another question. At a certain temperature, the degree of freedom per molecule for a gas is 8. So we have given F as 8. The gas performs 150 joules of work when it expands under constant pressure. Now the pressure is constant, right? And it performs 150 joules of work. So let us say work is 150 joules. It will be positive. Now the pressure is constant and the amount of heat absorbed by the gas will be. So we know that in isobaric process, when the pressure is constant, work done will be given by nR delta T. And this is nothing but 150 joules. And amount of heat absorbed by the gas will be. So in case of a isobaric process, the heat absorbed is given by NCP delta T. Okay, so this Cp can be written as F by 2 plus 1 times R times delta T. We'll study this Cp in the later part of the video. And so we can say F is given as 8 by 2 plus 1. NR delta T is 150. So this will be 5 into 150. So it comes out to be 750 joules. So that is the heat absorbed by the gas in this process. So 750 is the answer. Now let us see one more illustration. So again, we have given pressure volume graph, and here the graph looks like a circle, but it is not a circle because the unit on the x-axis, on the y-axis are different. On the y-axis, we have pressure in kilopascal. On the x-axis, we have volume in liters. Now, so we can say this figure is nothing but an ellipse. Now the area of an ellipse will be given by pi AB, where A is the semi-major axis and B is the semi-minor axis. So this length, so the major axis can be, we can say it will be 20 liters, and the minor axis will be 20 kilopascal, right? So if that is the case, we can say A is 10 liter, and it can be written as 10 times 10 raised per minus 3 meters, because 1 liter is equivalent to 10 raised per minus 3 liters. And B will be 10 kilopascals. So the work done in this cyclic process will be pi times AB. A is 10 into 10 raised per minus 3, and B is 10 into 10 raised per 3. So 10 raised per 3 will cancel out this 10 raised per minus 3, and we will get 100 pi joules, right? So 100 is the answer in this particular question. So in the next topic is internal energy of a gas, and internal energy we have already studied in kinetic theory of gases. Now this is the formula that we have to remember, F by 2 nR T. So this is the internal energy at a particular temperature, and we should always remember it depends upon the temperature and the type of gas, where F is a degree of freedom, which depends upon the gas. Now if we want to find the change in the internal energy, we have to use this formula, where we have, instead of T, we have to use change in temperature. So do remember these formulas. Now the next concept is the molar heat capacity at constant pressure and volume, and we'll also see for some other processes. So for constant volume, it is F by 2 R. Do remember this. And for constant pressure, it is F by 2 plus 1 times R. Now, basically, heat capacity is nothing but the heat supplied divided by N delta T. Now, this is a general formula of molar heat capacity. So, by using different processes, we can find the different values for C, and accordingly, we can find delta Q. So in case of a isothermal process, since delta T is 0 because there is no change in temperature in isothermal process, so molar heat capacity will become infinite. And for adiabatic process, delta Q is 0, so the molar heat capacity is 0. And for polytropic process, it will be given by F by 2R minus R upon A minus 1, where A is nothing but PV raised to power A equals to constant, right? So this is basically a polytropic process, where this A is not equals to gamma. So do remember this. Now let us see for different types of gases, what are the values of Cp, Cv and the value of gamma, right? So let us see. So Cv is given by this formula F by 2R, Cp is F by 2 plus 1 times R, and molar and gamma value is nothing but the ratio of these two molar heat capacity Cp by Cv. Now for monatomic gas, Cv value is 3 by 2R and Cp value is 5 by 2R. The ratio will be 5 by 3, which is 1.67. And for diatomic rigid molecules, it is 5 by 2R, Cp is 5 by 2R, and Cp is 7 by 2R. So the ratio will be 7 by 5, which is 1.4. And for polyatomic rigid non-linear molecules, it will be 3R, Cv will be 3R, Cp is 4R, and the ratio will be 1.33. So can you see as we are going down, the value of gamma is also decreasing, but it remains greater than 1. So do remember these values, because in questions you will be given the type of gas like monatomic, diatomic, polyatomic, and then by that particular given value you have to find the corresponding degree of freedom, and from that corresponding degree of freedom you can find Cp, Cv and gamma value. And there is one more formula for gamma. So we can say gamma is 1 plus 2 by F. So this formula is again very handy. You can remember this formula to find the gamma value if the degree of freedom is given to you.
Now let us see the questions based on the molar heat capacity. So here we have given two thermodynamic processes on the graph. The molar heat capacity for the process A and B is given as Ca and Cv. And we have also given the slope, right? So both the straight lines are passing through the origin, and on the y-axis we have given log P, on the x-axis we have given log V. The molar heat capacity at constant pressure and constant volume is given as Cp and Cv. So we have to choose the correct option, right? So let us see what we have given. So for the process A, if you take the slope, so what is the slope of this? It is given as, the angle is given as tan inverse gamma. So we can say tan times, say theta is the angle, right? Let us say this angle is theta. It is given as gamma. And this is also equals to log P upon log V, right? Because it is the slope. And from this we can say log P is equals to log V times gamma. And from this we can say log P is equals to log V raised to power gamma. Right? So if we compare left hand and the right hand side, we'll get PV raised to PV, P equals to V raised to power gamma. Or we can write this as P V raised to power minus gamma, which is constant. So that is the first process, A. Similarly, for the second process, the slope is given as like 1. So tan 45 will be 1. So we can say log P by log V will be 1 in the for the process B. So this is for process B and this is for process A. And from this we can say P will be equals to V. Or we can say P V raised to power minus 1 will be constant. Right? So now we know the relation between pressure and volume for both the processes. Now we have to compare Ca, Cv, Cb, Cp and Cv. So both the processes, so this is PV raised to power minus 1 is constant, PV raised to power minus gamma is constant. So they both are polytropic process. And in case of a polytropic process, molar heat capacity is given as F by 2 times R, which is nothing but Cv minus R upon N minus 1, where this N is this power, right? So here we have minus 1, here we have minus gamma. So we can say molar heat capacity in the first process, process A, will be given as F by 2 times R minus R divided by minus gamma minus 1. So this can be written as F by 2 R plus R upon gamma minus 1, right? And we know that this gamma value will be greater than 1 because the slope of the first A graph is more than the slope of the second graph, so gamma will be greater than 1, right? So we know that from the graph. So gamma is greater than 1. Now let us see the molarity capacity for the second process, and that will be F by 2R minus R divided by minus 1. So that will be F by 2R plus R by 2. Okay, sorry, here we have R plus 1, right? Not R minus 1. Gamma minus 1, gamma plus 1, sorry. Now if you compare CA and CB, the first term is same, but if you look at the second term, gamma is greater than 1. So we can say the denominator. So this denominator is greater than 2. So if the denominator is greater than 1, then this value itself becomes smaller. So we can say CB is greater than CA, right? So we got this. And what is CV? CV is F by 2R. So we can say CV is less than CB and as well as from CA, right? And what is CP? CP is F by 2 times R plus R. Right, so what we can say, Cp is greater than all the molar heat capacities, so we can say Cp will be greater than Cb, and Cb will be greater than Ca, and Ca is greater than Cv. So that should be the correct order. So if you look at the option 4 is the right answer. Not option 4, option 3. Right, so let us see the next question. 2 moles of a monatomic gas is mixed with 6 moles. So 2 moles are mixed of monatomic gas are mixed with 6 moles of diatomic gas. The molar specific heat of the mixture at constant volume. So basically we have to find CV for the mixture. And which formula we can use? It will be N1CV1 plus N2CV2 divided by N1 plus N2, where N1 is 2 moles, N2 is 6 moles, CV1 for a monatomic gas, it will be 3 by 2R, and CV2 for a diatomic gas will be 5 by 2R. Now let us substitute these values. So it will be 2 times 3 by 2R plus 6 times 5 by 2R divided by 2 plus 6, and this 2 will get cancelled out with this. It will give us 3, so it will be 3 plus 15, 18 R by 8, which comes out to be 18. Yes, so this will be 15 plus 3, 18 divided by 8, so it comes out to be 9 by 4 R. So option 1 is the right answer. Now let us see the next question. The specific heat at a constant pressure of a real gas obeys this law, PV square is equals to RT. Then okay, right, so it is at constant pressure we have to find. So pressure is constant, so let us find the molar specific heat. We know that if you apply first law of thermodynamics, it can be written as dq is du or du plus dw. And in case of a constant pressure, work done can be written as, so we can write work done as P dV. And the change in internal energy can be written as CV times dt, and dq it can be written as C times dt. Right, so from this equation, so we can say C dt is equals to CV dt plus P dV, right? And if you look at the option, we have given answers in terms of CV and R, and volume is also there, right? So let us try to find the value of dV in terms of dt, because we want to eliminate dt. So if you look at this relation, if I differentiate this, pressure is constant, so if you differentiate this, so we can say it will be P times 2V dV, because the differentiation of V square will be 2V with respect to V only, right? But if with respect to some other variable, it will be 2V dV by that particular dt of that variable, right? So this can be written as R times dt. So from this we can say P dV can be written as R dt upon 2V. So now let us substitute this value in this equation. So we will get C dt is equals to CV times dt plus R dt upon 2V. Now from this equation we can eliminate dt, right? And can you see the option 3 is the right answer. So here we have found the molar heat capacity for that particular process. Now let us the next question. A mixture of 1 mole of monatomic gas and 1 mole of diatomic gas are kept at a room temperature 27 degrees Celsius. The ratio of specific heat of gases at constant volume. So basically we have to find the ratio. So CV1 upon CV2 we have to calculate, where 1 stands for this monatomic gas and 2 stands for this diatomic gas. Now for monatomic gas, the CV, the formula for CV is F by 2R, and for monatomic the value of degree of freedom in case of monatomic gas is 3, and for rigid diatomic it will be 5. So it will be 3 by 2R upon 5 by 2R. So the answer comes out to be 3 by 5. So option 2 is the right answer. Now let us see the problem type based on the concept of internal energy. So we have given 0.8 kilogram air is heated at a constant volume through 5 degrees Celsius. So the increase in temperature is 5 degrees Celsius. The specific heat of the air at constant volume is given as 0.17 kilocalorie per kilogram per degree Celsius, and the joules um, and J value is given as 4.18 joules per calorie. And the change in the internal energy is approximately. So we have to find delta U. So let us see. And it's a constant volume process. So in case of a constant volume, work done will be 0. So delta Q will be equals to delta U. So if you are able to find delta Q, we'll be able to find the change in internal energy. And delta Q can be written as M S delta T, where S is the specific heat capacity at constant volume. So mass is given as 0.08 and the specific heat capacity is given as 0.71 kilocalorie per kilogram per degree Celsius, or I can write this as 170 calorie. 170 calorie per kilogram per degree Celsius multiplied with the change in temperature, which is 5, right? And we have to convert this into SI units. So 1 calorie is equivalent to 4.18 joules. So that should be the change in internal energy. And if we simplify this, it comes out to be 284 joules. So that should be the answer of this question. Right, so let us see the next question based on the same concept. A gas mixture contains 8 moles of argon, 6 moles of oxygen. At temperature T, neglecting all vibrational modes, the total internal energy of the system. So we have to find the internal energy, and we have given a mixture of gas. So let us say N1 is given as 8, N2 is 6, and the first gas is a monatomic gas, the other gas is the diatomic gas. Now the internal energy corresponding to the first gas will be 3 by 2 N RT, right, where the formula for internal energy is F by 2 nRT. So basically you have to add up the internal energy for both the gases plus, and for diatomic gas the value of F is 5, so 5 by 2 6 RT. So this will give us 3 and we'll get 4 here, so it will be 12 plus 15 RT. So which comes out to be 27 RT. So option 3 is the right answer.
So 1 mole of an ideal monatomic gas undergoes a process described by the equation PV raised to power 3 equals to constant. The heat capacity of the gas during this process is now PV raised to power 3. So we know that molar heat capacity for a polytropic process will be given by F by 2R minus R upon A minus 1. Now here the value of A is 3. So and it is a monatomic gas. So in case of a monatomic gas, the degree of freedom is 3. So it will be 3 by 2 R minus R upon 3 minus 1. So that will become 2R by 2, 2R by 2, and it is nothing but R. So option D is the right answer. Now let us see some of the illustrations based on these concepts. So 1 mole of a monatomic gas is mixed with 3 moles of diatomic gas. So basically we have a container. In this container, we have monatomic gas and we have diatomic gas, right? So for monatomic, we have 1 mole, and for diatomic we have given 3 moles. Let us say N1 is 1 and N2 is 3. The molar specific heat of a mixture at a constant volume. So, so at constant volume, it is given as alpha square by 4 R. And we know that Cv is nothing but F equivalent by 2 R. So when we have more than one gas in a container, we have to find equivalent degree of freedom. And this equivalent degree of freedom will be N1 F1 plus N2 F2 divided by N1 plus N2. It is the weighted mean for the degree of freedoms, right? So for monatomic gas, F1 is 3, and for rigid diatomic molecules, F2 will be 5. If nothing is given about that, okay, right. And in the if you look at the last statement, it says assume that the given diatomic gas has no vibrational mode, means we have a rigid diatomic molecules. So the degree of freedom will be 5. So N1 is 1, F1 is 3, N2 is 3, and F2 is 5. So 1 plus 3. So this will be 18 by 4, which is 9 by 2. So we can say it is 9 by 4 R. So if I compare this and this, we can say alpha is 3. So 3 is the answer. Now let us see one more question. The amount of heat needed to raise temperature of 4 moles of rigid diatomic gas from 0 degrees Celsius to 50 degrees Celsius. So we want to increase temperature from 0 to 50. And we have given n equals to 4. And when no work is done. So when no work is done, it means we have a isochoric process. Isochoric process. So volume will remain constant. So in case of a constant volume, and the amount of heat needed will be N CV delta T, right? N CV delta T. And temperature is increasing, and it's a, yeah, so 4 moles is given to us. So it will be 4, and CV is F by 2 R delta T. And we have to find answer in terms of R. And what type of gas we have given? Rigid diatomic. So degree of freedom will be 5. So it will be 2 times 5 times R, and that increase in temperature is 50. So that will become 500 R. So 500 R is the answer. Right. So now let us see the another concept, that is first law of thermodynamics. So what is this law? Suppose if there is a thermodynamic system and you are supplying delta Q amount of heat energy, some part of this energy will increase the internal energy and the remaining part will do the work done. Now, this delta Q will be positive if we are supplying heat to the thermodynamic system. It will be negative if the heat is being rejected from the system. And work done will be positive if there is an expansion of the gas, and it will be negative if there is a compression. And internal energy will increase if the temperature of the gas is increasing, and it will decrease if the temperature is decreasing. So do remember these nomenclature, because in question they will give you like the internal energy is increasing. So from that you have to figure out the temperature is increasing or decreasing. It will increase, right, if delta U is increasing. Okay, right. So let us see an illustration. A source applied heat to a system at a rate of 1000 watt. So basically delta Q by delta T is given as 1000 watt. If the system performs work at a rate of 200 watt, so delta W by delta T is given as 200 watt. The rate at which the internal energy of the system increases. So we know that delta Q is equals to delta U plus delta W by first law of thermodynamics. So if I divide both sides by delta T, which is the change in temperature, we will get the rate at which the heat is applied on the left hand side, right? So this will be 1000, and delta U by delta T we have to calculate, plus 200. So the answer will be nothing but 800 watt. Okay, now let us see one more question. A monatomic gas performs a work of Q by 4, where Q is the heat supplied to it, and the molar heat capacity of the gas will be dash times R during this transformation, where R is a gas constant. So basically we have to find the molar heat capacity for this particular process. So we have given Q, the heat supplied, and by first law of thermodynamics, and work is also given, right? So delta W is given as Q by 4. So we can say delta U will be Q minus delta W, which will be Q 3 Q by 4. Now that is the change in internal energy. And we know that change in internal energy formula is F by 2 nR delta T, which will be 3Q by 4. And molar heat capacity, the general formula is the heat supply divided by N delta T. So if we know the value of N delta T in terms of Q, we can find the molar heat capacity. So from here, we can say, yeah, so so from this equation, we have nR delta T, right? So this nR delta T, and we have given a monatomic gas. So F will be 3. So 3 by 2 nR delta T is equals to 3Q by 4. So this 3 will get eliminated and this will give us 2 here. So we can see that N delta T is Q by 2N, right? Q by 2N. Now if I substitute this value in this equation, so it will be Q by 2N. And there is a N delta T, right? Oh, sorry, this N will not be there. So it comes out to be 2 times R, right? So the answer will be 2. I hope this concept is clear to you, right? So now let us see the another illustration. A sample of an ideal gas is taken through the cyclic process ABCA as shown in the figure. It absorbs 40 joules of heat during the process AB. So we have given delta Q A to B as 40. So it absorbs, so it will be plus 40, right? Plus 40 joules. And no heat during BC. So delta Q from B to C is 0. And it rejects 60 joules of heat during CA. Rejects means the heat is rejected out, so it will be negative. C to A, it will be minus 60 joules. And a work of 50 joule is done on the gas during the part BC. So work done for the part BC will be work done on the gas. So work done on the gas means the work done is negative. So minus 50 joules. And the internal energy of the gas at A is 1560 joules. The work done by the gas during the part CA. Okay. Now in a cyclic process, since we are coming back to the same initial state, there is no change in the internal energy. So delta U will be 0 for the cyclic process. And the work done will be given by work done from A to B plus work done from B to C plus work done from C to A. Since A to B is a isochoric process, A to B is a isochoric process, there is no change in the volume. So this work done A to B will be 0. And we have given work done from B to C, and this is nothing but minus 50. So we can say by first law of thermodynamics, delta Q will be sum of all these heat exchange, right? So plus 40 plus 0 minus 60. So it comes out to be minus 20 joules. So by first law of thermodynamics, we can say delta Q will be equals to delta U plus delta W. Delta Q is minus 20, delta U is 0, and work done will be delta W from C to A minus 50. So delta W from C to A is nothing but 30 joules. So option B is the right answer. Now let us see the another concept, that is the different types of thermodynamic processes. So we'll cover all the processes. First we'll cover isothermal, then isobaric, isochoric, then adiabatic, polytropic, cyclic process. So one by one, right? So isothermal process. So in isothermal process, there is no change in the temperature. So delta T will be 0. If delta T is 0, we know delta U is F by 2 nR delta T. So delta U is also 0. So if we apply ideal gas equation, if temperature is constant, PV is also constant. So for a given amount of gas, so P1 V1 is equals to P2 V2. And if delta U is 0, we can say delta Q will be equals to delta W by first law of thermodynamics. And in isothermal process, the work done is nRT ln V2 by V1, or we can also replace V2 by V1 with P1 by P2. So it will be nRT ln P2 P1 by P2. Now, if we show the indicator diagram, let us say on the y-axis we have pressure, on the x-axis we have volume. Can you see? So as the volume increases, pressure will decrease because P is inversely proportional. So P is inversely proportional to volume. So the graph will look like this. let us say at this particular graph, in this expansion, the temperature is T1. And let us say there is another graph. At this graph, the temperature is T2. And for this graph, the temperature is T3. So these graphs are known as isotherms, right? So these are isotherms, same temperature. On these graphs, the temperature will remain same. And so in this particular case, T1 is less than T2 is less than T3, right? So do remember this. If we want to find the slope to this graph, let us say this point, the volume is say V naught and the pressure is P naught and the slope is this, right? So this angle is theta with the positive x-axis. So tan theta is nothing but dP by dV and it will be given by minus P naught by V naught, right? So do remember this formula for slope. Now let us see the volume versus temperature. So in this case, if we plot volume versus temperature, we know temperature is constant, so the graph will be something like this. Okay, so if volume is increasing, so pressure will decrease in this process. And if we plot volume versus pressure, volume versus temperature versus volume, in this case, it will be something like this. It will be parallel to the volume axis because the temperature is constant. So if the volume is increasing, pressure should decrease. Okay, this is the same graph. Okay, let me plot the graph between pressure and temperature. Pressure and temperature. So it will be something like this. So as the pressure increases, volume will decrease. So we can say it is a graph of compression. Okay, so these points, these concepts you have to remember for isothermal process. Now let us see some of the illustration based on isothermal process. So we have given 1 mole of an ideal gas at 27 degrees Celsius is taken from A to B as shown in the given PV indicator diagram. The work done by the system will be, so since the temperature is constant, we can apply this formula nRT ln V2 by V1. So here number of moles is given as 1 and R value is 8.3 and temperature is 300 Kelvin. If we convert 27 degrees Celsius into Kelvin, we have to add 273. And volume, final volume is 4 meter cube. Initial volume is 2 meter cube. So we can say 4 by 2. So this will be 8.3 times 300 times ln 2. And this natural log 2 is nothing but 0.6931. So 8.3 times 300 times 0.6931. So if we simplify this, we will get around 17258. That is the answer to the nearest. So basically it will be 1725.8, right? Which can be written as 17258 into 10 raised per minus 1. So the answer will be 17258. Okay, now let's see another illustration. The thermodynamic process in which internal energy of the system remains constant. So internal energy remains constant means delta U is 0. Delta U is 0 when delta T is 0. So it means in case of an isothermal process, the internal energy will not change. Let us see one more illustration. In an isothermal change, the change in pressure and volume of a gas can be represented from 3 different temperatures, where T3 is greater than T2 is greater than T1. We have just studied this concept. So the answer will be option 4. Right? Let us see one more question. Given below are 2 statements. Statement 1, if heat is added to the system, its temperature must increase. Okay. So we know that in isothermal process, delta T is 0, but we know that delta Q can be non-zero. So we can supply heat energy and delta Q can be positive, but still there is no change in the temperature. There is no increase in the temperature. So statement 1 is incorrect. Now, if positive work is done by the system in a thermodynamic process, its volume must increase. Yes. So when there is an expansion, work done by the gas is positive. So statement 2 is correct. So statement 1 is false, but the statement 2 is true. So option 4 is the right answer. Right. So now let us see the other process, that is isochoric process. So in isochoric process, volume remain constant. So delta V will be 0. If delta V is 0, we know if there is no change in the volume, work done will be 0 by the gas. If we apply ideal gas equation, say if volume is 0, P is directly proportional to T, so we can write P1 by T1 equals to P2 by T2. And in case of an isochoric process, heat supplied to the gas can be given by NCV delta T, where CV is nothing but F by 2R. So we should remember this. It is F by 2 NR delta T in case of a isochoric process. Now, if we plot pressure volume graph for isochoric process, since volume remains constant, it will be a graph which is parallel to the y-axis. Let us say the pressure is increasing. If pressure is increasing, temperature will also increase. So this is the graph for increase in temperature. Now, if we plot pressure versus temperature, now in this case, pressure is directly proportional to temperature. So we can say the graph will be a straight line passing through the origin. Okay, I'm showing two processes. So say for this particular process, the volume is V2, and for this process, the volume is V1, since both these curves are for isochoric process. Now the question is which one is greater, V1 or V2? So by ideal gas equation, PV is equals to nRT, and it can be written as P equals to nR by V times T. Now this nR by V is nothing but the slope. For a given amount of gas, if we have a greater volume, then the slope will be less, right? So I'm considering the two isochoric process for same amount of gas. So can you see this angle theta 1, and let's say this angle is theta 2. Now theta 1 is less than theta 2. It means V1 is greater than V2, because smaller the angle, smaller the slope, more is the volume. So V1 is greater than V2. So again, remember this. Now if we plot temperature and volume, so on the y-axis we have temperature, on the x-axis we have volume. So can you see it's a isochoric process. Again, it is a graph which is parallel to the y-axis. So if the temperature is increasing, pressure will also increase. Do remember this. Now let us see the isobaric process. So in isobaric process, the pressure remains constant. So delta P will be 0. And if delta P is 0 or P is constant, by ideal gas equation, we can say V1 by T1 equals to V2 by T2, or V is directly proportional to temperature. Now, work done in isobaric process will be given by P delta V, which is nR delta T, and the heat supplied will be NCP delta T, and we have just seen Cp value, that is F by 2 plus 1 times R. So we should remember this. And if we show the indicator diagram, say pressure and volume indicator diagram, in isobaric process, it will be a graph which is parallel to the x-axis. So if the volume is increasing, temperature will also increase, because volume is directly proportional to the temperature. And in pressure temperature graph, again it will be a graph which is parallel to the x-axis. If the temperature is increasing, volume will also increase, so we can say there will be expansion. In case of a compression, the arrow direction will get reversed. Now if we plot temperature versus volume, in this case temperature and volume, they are directly proportional to each other, so it will be a graph which is a straight line passing through the origin. So if this is P1 and this is P2, if in both these isobaric process, if the amount of gas is same, we can say P1 will be greater than P2.
Now let us see question based on the concept of isobaric process. So here we have given a diatomic gas, gamma value is given 1.4, does 200 joules of work when it is expanded isobarically. So it's a isobaric process. The heat given to the gas in the process. So we have to find the heat supplied to the gas. Work done is given. So delta W is given as 200 joules. And it's a isobaric process. And we know that in isobaric process, work done can also be written as nR delta T. So this can also be written as nR delta T. And we have to find heat. So delta Q in isobaric will be F by 2 plus 1 and nR delta T, right? Where F by 2 plus 1 R is nothing but Cp, molar heat capacity at constant pressure. Now this nR delta T is nothing but 200. And for a diatomic gas, gamma value is given as 1.4. So it means this Cp is nothing but 7 by 2R. So F by 2 plus 1 times R is nothing but 7 by 2 R and delta T, and this value is nothing but 200 joules. So 7 by 2 times 200, it will give us 700 joules. So that is the heat supply to the gas. So option 4 is the right answer. Now let us see another question based on the same concept, but in this question they have given 100 joules of work. Can you see this question is very similar to last question? By using the same concept, we'll get the answer as 3, which is 350 joules. Now let us say this question based on the isobaric process. So the given figure represents two isobaric process for the same mass. So mass is same. There is no change in the mass. Then, and we have given volume is proportional to temperature. So it means pressure is constant. So we can say V is equals to nR by P times T, right? Now if you look at the slope of this graph, it will be governed by nR by P. So if slope is inversely proportional to the pressure, if the pressure is more, slope will be less. So it means P1 is greater than P2 because the slope of this graph is less than the slope of this graph. So P1 is greater than P2, so option 4 is the right answer.
For a perfect gas, two pressures P1 and P2 are shown in the graph, in the figure. Okay, so the graph shows, okay, right. So P1 and P2 is given, and both these graphs are passing to the origin. Basically, this is a question for isobaric process, but still we can cover this. So in isobaric, pressure remains constant. So you can say volume is directly proportional to temperature, and we can say V is equals to nR by P times T. So for a given amount of gas, if slope is inversely proportional to the pressure, so smaller the pressure, more will be the slope. So we can say P2 is less than P1. So option A is the right answer. So we have given n moles of a perfect gas undergoes a cyclic process ABCA consisting of the following processes. From A to B, there is a isothermal process where volume is increasing from V1 to V2. V1 to 2V2. Sorry, V1 to 2V1. And then from B to C, we have a isobaric process, right? It's an isobaric process where volume is decreasing from 2V1 to V1. And then there is an isochoric process, C to A, where pressure is increasing from P2 to P1. Now we need to find the total work done in the cyclic process. And we have given n moles, right? So can you see there are three processes, A, B, B, C, and C, A. So work done in the process A to B, which is a isothermal process. So it will be nRT ln 2, right? Because volume is getting double. So it will be nRT ln 2. Now work done from B to C. So in a isobaric process, work done will be given by P delta V or nR delta T, right? So we can write this as nR, or you can say it will be, I can write this as P delta V, right? Pressure at B is, let us say, P2 and P2, and volume is, final volume is V1 and initial volume is 2V1. So this is nothing but minus P2 V1. Okay, so since A and B are 2 points on the same isotherm, so we can say P1 V1 is equals to P2 2V1, right? So we can say P2 is half of P1, right? And by ideal gas equation, if I apply ideal gas equation for A, so we can say nRT equals to P1 V1. It is also equals to nRT equals to P2 2V1, right? So P2 2V1 can be written as minus nRT by 2. So do remember this. So from C to A, it's a isochoric process, so work done will be 0. So overall work done will be what? It will be nRT ln 2 minus nRT by 2. So this is nRT will be common, so it will be ln minus 1 by 2. So option 4 is the right answer. Now let us see one more illustration. A diatomic gas where gamma value is given as 1.4 does 400 joules of work when it is expanded isobarically. So delta W is given as 400 joules. gamma value is 1.4, and it is expanded isobarically, the heat given to the gas in the process. So we know that delta Q for a isobaric process is NCP delta T, and Cp can be written as F by 2 plus 1 times R, and we know that 1 plus 2 by F is equals to gamma. So I can say 1 plus 2 by F is equals to 1.4, and 2 by F is 0.4, and F by 2 will be 1 upon 0.4, which is 5 by 2. So I can put this value here. So N times 5 by 2 plus 1 times R delta T. And we know that in case of isobaric process, work done is given as nR delta T. So nR delta T value is 400 joules. So it will be 7 by 2 times 400. So that will be 1400 joules. So 1400 is the answer. Now again, very important process, adiabatic process. So in adiabatic process, it's a very fast process where changes happens at a very fast rate. Here delta Q is 0 because there is no time to exchange heat with the surrounding for the system. So delta Q is 0. Delta Q is 0. We can see delta U. Sorry, delta Q is 0. And in isobaric process, PV raised to power gamma is constant, where gamma is Cp by Cv, right? And we can also write, if I want to find a relation between pressure and temperature, I can write P raised to power 1 minus gamma times T raised to power gamma equals to constant, or we can further simplify this, where Pt raised to power gamma upon 1 minus gamma. So that is constant. And Tb raised to power gamma minus 1, right? So you should remember these proportionalities. And work done in adiabatic process will be given by this formula. And we have already studied this formula, right, in the section of work done. Now, if I plot pressure volume graph for adiabatic process, so PV raised to power gamma, right? Now, and we know that gamma value is greater than 1. So you can see if we increase the volume, the pressure will decrease. So the graph will be something like this, right? And suppose if I want to find the slope at this particular point where the volume is V naught and the pressure is P naught. So this slope will be given by minus gamma P by V, right? Minus gamma P naught by V naught. So can you see, if I compare the slope of adiabatic curve and the isotherm, there is a difference. There is a additional factor in the slope of adiabatic curve, that is gamma. So we can, and gamma value is greater than 1. So we can say the slope, we can say the graph will be for a particular state, the graph will be steeper. For example, if I have, so this is P axis, this is V axis, and let us say this is a isotherm, right? So at this particular point, the slope to a adiabatic will be, or you can say the tangent will be more steeper, right? Adiabatic. So like from this, we can identify the two different processes, right? We can easily figure out which process is adiabatic by looking at the steepness. Okay, now this is again very important section where we will expanding a gas from a same initial state by different processes. Now, I suppose we have started from this particular state. This is the initial state, and the initial volume is V1, and the final volume is V2. So we're expanding from V1 to V2. So this is the isobaric process. So we are going in this direction. And this is a isothermal process, isothermal expansion. And this is a adiabatic polyatomic gas, right? Here, the degree of freedom I've taken as 6. And this is a diatomic gas where degree of freedom I have taken as 5. And for monatomic gas, the degree of freedom will be 3. So can you see, for monatomic gas, the gamma value is 1.67, and for diatomic gas, the gamma value is 1.4, and for polyatomic, the gamma value is 1.33. So, and you can easily figure out from their slopes, right? So for adiabatic, the steepness is the smallest, but in case of mono, it is the greatest, right? Steepness is the greatest at this particular point. So we can say, suppose if W1 is the work done in the isobaric process, W2 is the work done in the isothermal, and W3 in the adiabatic polyatomic gas, and W4 is the work done in the adiabatic diatomic gas, and W5 is the work done in adiabatic monatomic gas. So the area under the graph, so on the y-axis we have pressure, on the x-axis we have volume. So the area under pressure volume graph is greatest in case of isobaric process, and it decreases as we are going down, right? So work done in the isobaric process will be greater than, so W1 will be greater than W2, and W2 will be greater than W3. So this is the decreasing order of work done by a gas. Now, if we want to find the compression and we are starting from the same initial state, let us say this is our initial state and the volume is say V2, and we are going to a volume V1 like this, right? So this is the isobaric process. Then we have isothermal process, and then adiabatic polyatomic gas, and then diatomic, and then monatomic. So this is the curve, right? So for the compression part, can you see again the areas? In this case, the area under adiabatic monatomic gas is greatest, but since there is a compression, so the work done will be negative. But suppose if suppose in the question they ask you the magnitude of the work done in different processes, so we can say the magnitude of the work done in adiabatic monatomic gas will be greatest. Got it? Because the area under the curve is greatest. But if you talk about in terms of the actual algebraic value with proper sign, in that case, again, the work done by the isobaric process will be greatest because it will be least negative. Got it? So do remember these graphs.
Now let us see the illustration based on the adiabatic process. So a sample of 1 mole of gas at temperature T is adiabatically expanded to double its volume. If the adiabatic constant for the gas is 3/2, then the work done by the gas in the process. Now in adiabatic process, work done is given as P1 V1 minus P2 V2 divided by gamma minus 1. And here we have given 1 mole and temperature is given, initial temperature is given, and we have given the volume has been doubled. So we need to find what is the final temperature. So what we can do, we can use this proportionality that T V raised to power gamma minus 1 must be constant in case of adiabatic process. So we can say T V raised to power gamma minus 1 must be equals to T prime. T prime is the final temperature, sorry, and it will be 2 times V because volume is getting doubled, gamma minus 1. So we can eliminate V. So from this, T prime will be T divided by 2 raised to power gamma minus 1, and gamma value is given as 3/2. So this 3/2 minus 1 will be 1/2. So that will be T by root 2. Now let us, and we can also write work done as NR T1 minus T2, right, upon gamma minus 1. So that is the work done. So work done can be written as N is 1, number of mole is given as 1, R T1 is nothing but T, and T2 is nothing but T by root 2. Divided by gamma minus 1, gamma is 3/2 minus 1, so it comes out to be 2 times R times root 2 minus 1 times T by root 2, or which can be written as root 2 R root 2 minus 1 times T, and we can also write this as RT 2 minus root 2. So that is the work done. So option 3 is the right answer. Now let us see this question. Again, it is same question, right? So we'll get the same answer. So option 3 is the right answer. So can you see there is a repetition of the same question in 2 different shifts? So that's why whenever you appear for your shift, it is always recommended to see the questions which have come in earlier shifts. Right. So let us see this question. Choose the correct statement for the processes A and B. So we have given 2 processes, and we have given some options. PV raised to power gamma is constant for process B, and PV raised to power PV equals to constant. PV raised to power gamma is constant means it's an adiabatic process. If PV equals to constant means it's an isothermal process. So nowhere it is mentioned what type of process it is. So here I'm going to use an assumption. Without this assumption, we cannot solve this question. In case of a adiabatic process at a particular pressure and volume, the slope to an adiabatic process is always greater than the steepness, you can say. dP by dV for an adiabatic process, its modulus is greater than dP by dV for isothermal process. right? So if you look at this point, let me call this point as C. At C, the slope to B curve is more steeper than the slope to A curve. So we can say this B curve is adiabatic and this A curve is isothermal. So that assumption we have to take, one of the process is isothermal, other is adiabatic. So process A is isothermal, so PV should be constant, and process B is adiabatic, so it will be PV raised to power gamma is constant. So option 1 is the right answer. Right, so let us see the next question. During an adiabatic process, the pressure of gas is found to be proportional to the cube of temperature and the value of Cp by Cv for the gas. Okay, so we know we have given P is proportional to T raised to power 3, right? And we have to find the value of gamma. Okay, so one thing you can do, you can write T in terms of pressure and volume. So we know that T is proportional to PV. So I can write this as P as proportional to PV raised to power 3, because T will be proportional to PV in case of a real gas, ideal gas. So this can be written as P is proportional to P cube V cube. So this can be written as P square V cube must be constant. And from this we can say PV raised to power 3 by 2 must be constant, right? Now from this relation we can say the gamma value will be given by the power of V. So 3 by 2 is the answer of this question. Right, so let us see the next question. If 3 moles of monatomic gas, gamma is given, is mixed with 2 moles of diatomic gas, gamma is given, the value of adiabatic constant gamma. So we have to find the value of gamma for the mixture. So that is nothing but Cp of mixture divided by Cv of mixture. And Cp of mixture will be N1 Cp1 plus N2 Cp2 divided by N1 plus N2, and Cv of mixture will be N1 Cv1 plus N2 Cv2 divided by N1 plus N2. So we can say gamma of mixture will be given as N1 Cp1 plus N2 Cp2 divided by N1 Cv1 plus N2 Cv2. Now in case of a monatomic gas, this Cp1 for monatomic will be 5 by 2R, and for diatomic Cp2 will be 7 by 2R. Similarly, and this Cv1 and Cv2 for monatomic, Cv1 will be 3 by 2R and Cv2 will be 5 by 2R, and N1 N2, their values are given in the question. So N1 is 2 moles, sorry, N1 is 3 moles, N2 is 2. This is 3, this is 2. Now if you simplify this, we will get 15 plus 14 divided by 9 plus 10. Because r by 2 will get cancelled out from the numerator and the denominator. This comes out to be 29 by 19, and which is close to 1.52. So option 3 is the right answer. Right, so let us see the next question. During an adiabatic process, if the pressure is found to be proportional to cube, again there is a repetition of the same question, similar question. Then the ratio of Cp by Cv, right? We have seen and done the same question, so you can do this on your own, and the answer is 3 by 2. Right, so let us see this question. The volume of an ideal gas whose gamma value is given as 1.5 is changed adiabatically from 5 liter to 4 liter, the ratio of initial pressure to the final pressure. So here we can use this proportionality, that P1 V1 raised to power gamma is equals to P2 V2 raised to power gamma in case of a adiabatic process. Let us plug in the value. So volume is given, right? So this will be V1, this will be V2, and we have to find the ratio of initial pressure and the final pressure. So P1 by P2 will be V2 by V1 raised to power gamma, which is 3 by 2. So it will be 4 by 5 raised to power 3 by 2, and 4 raised to power 3 by 2 upon 5 raised to power 3 by 2. This can be written as 8. This will be 5 root 5. So option 3 is the right answer.
Now let us see the illustration based on these concepts. A gas is compressed adiabatically, which one of the following statement is not true. So volume is decreasing. So there is no heat supply to the system. Yeah, this is the definition of adiabatic process. There is no heat exchange between the system and surrounding. So option 1 is a true option. So this is not our answer. The temperature of the gas increases. Now let us understand this. So the relation between the volume and the temperature is Tv raised to power gamma minus 1 is constant. Now gamma minus 1, this value is positive. So if volume decreases, if this decreases, then the temperature will increase. So option 2 is again correct. So this is not our answer. Now the change in the internal energy is equal to the work done on the gas. Now work done, that if delta W is work done by gas, then I can say minus delta W will be work done on gas. And we know that delta Q is 0 in adiabatic process. So delta W plus delta U will be 0. So minus delta W will be delta U. So we can say work done on the gas will be nothing but the change in internal energy. So this is again correct. So this is not our answer. So there is no change in the internal energy. So this is incorrect, right? This is not true. So option 4 is the right answer because internal energy will change, only delta Q is 0, right? So option 4 is the right answer. Now let us see another question. It came in 2022. Statement 1 is when mu amount of an ideal gas undergoes an adiabatic change. So this mu is nothing but the moles, right? From a state P1, V1, T1 to state P2, V2, T2. The work done. So when only work done is given in a statement, you always take it as work done by a gas, right? So work done by a gas is mu R T2 minus T1 upon 1 minus gamma. Yes, so that is correct. Okay. And where gamma is Cp by Cv. So statement 1 is correct. Now statement 2, in the above case, when work is done on the gas, the temperature of the gas would rise. So work is done on the gas. So it states that minus W will be mu R T2 minus T1 divided by gamma minus 1. Now if there is a work done on the gas, so this value is positive, then we can clearly see that the temperature will also increase because gamma minus 1 is positive. So if left hand side is positive and so the right hand side has to be positive, so T2 minus T1 will be positive. So delta T is greater than 0. So temperature of the gas would rise. So statement 2 is again correct. So we can say statement 1 and statement 2 both are correct. So option A is the right answer. So let us see this question. So we have given starting with the same initial conditions, an ideal gas expands from volume V1 to volume V2 in 3 different ways. The work done by the gas is W1 if the process is isothermal. So W1 in case of isothermal process. W2 is the work done in case of a purely adiabatic process. And W3 is the work done in purely isobaric process. So we have to find the increasing order of work done. Okay, so we have already studied this concept. So if I plot these processes, so let us say on the y-axis we have pressure, on the x-axis we have volume, and we are expanding from V1 to V2. So let us say this is the starting state. So this is the isobaric process. So in this case, the work done is given as W3, and then we'll be having isothermal, that will be W1, and then adiabatic, so that is W2. So we can clearly see that work done in W3 is the greatest because the area under the graph, pressure volume graph is greatest. So in the increasing order, we can say W2 is less than W1 and W1 is less than W3. So 2, 1, 3. So option D is the right answer. Now let us see another question. A certain amount of gas of volume V at 27 degrees Celsius temperature and pressure 2 into 10 raised by 7 Newton per meter square expands isothermally. So it's an isothermal process, right? Until its volume gets doubled. So volume is increasing. So let us say initial volume is V and then it becomes 2V, and we have given initial pressure which is 2 into 10 raised per 7, and The temperature is also given, that is 27 degrees Celsius. Later it expands adiabatically until its volume gets redoubled. Okay. So from V to 2V, it is isothermal, right? And then from 2V to 4V, it's a adiabatic, right? Until its volume gets redoubled. The final pressure of the gas will be, okay, so we have to find the final pressure. Let me just plot the graph. So let us say this is P, this is V. We have started from this particular state. So first it expands isothermally from V to 2V, and then it expands adiabatically from 2V to 4V, right? So let me show it with different colors. So this is adiabatic, right? This one is adiabatic expansion, and this white one is isothermal expansion. Let us say this is A, this is B, and this is C. And at A, the pressure is given as 2 into 10 raised per 7. Okay, so can we find the pressure at B? Yes, we can find pressure at B, because for isothermal process, P1 V1 is equals to P2 V2. So we can say 2 into 10 raised per 7 V equals to pressure at B times 2V, right? So pressure will become half. So it becomes 10 raised per 7 Newton per meter square. Okay, so since from B to C we have a adiabatic process. So in adiabatic process, we know that PV raised to power gamma is constant, and gamma value is given as 1.5 in the question. So we can say PB 2V raised to power 1.5 is equals to PC 4V raised to power 1.5. Now this V will get eliminated, and PB is 10 raised to power 7. So we can say PC is equals to 10 raised to power 7 times 2 by 4 raised to power 1 point, or you can say 3 by 2, right? So this will become 2 in the denominator. So we have to find the pressure. So this will become 10 raised to power 7 divided by 2 root 2, right? So this can be written as, so let me write here. So PC will be, you can write it as root 2 upon 4, 10 raised to power 7. So which is nothing but 1.414 by 4 into 10 raised to power 7. And this is 0.3536 into 10 raised to power 7. And I can write this as 3.536 into 10 raised to power 6 Newton per meter square. So if you look at the option, option B is the right answer, right? Option B is the right answer. Right, so now let us see the another question. The pressure P1 and density D1 of diatomic gas, where gamma value is given, changes suddenly to P2, where P2 is greater than P1 and D2. Density becomes D2, respectively during a adiabatic process. So it's an adiabatic process. The temperature of the gas increases and becomes a dash times its initial temperature. So we have to find the relation between initial and the final temperature, and the ratio of the density final to the initial is given as 32. Okay, so since density ratio is given, first of all we have to find the relation between the temperature. So we have to find the relation between temperature and density, right? Okay, so we know that P m naught is equals to rho RT, right? And we can write P, and we know that in adiabatic process, P raised to power 1 minus gamma and T raised to power gamma is constant. So we can say P can be written as P times T raised to power gamma by 1 minus gamma is constant. So I can say it will be T raised to power gamma upon 1 minus gamma is directly proportional to rho T. 1 by, so P can be written as 1 by T raised to power gamma upon 1 minus gamma. So let us simplify this. Rho T 1 plus gamma upon 1 minus gamma is constant. So this can be written as rho T, and this will be 1 upon 1 minus gamma, right? So these are the this is the relation between the density and the temperature. So I can say D1 T1 raised to power 1 upon 1 minus gamma. Gamma is 7 by 5, right? So 7 by 5 is equals to D2, T2, 1 upon 1 minus 7 by 5. So 1 upon 1 minus 7 by 5 is nothing but minus 5 by 2. So D1 or D2 by D1 is equals to T1 by T2 raised to power minus 5 by 2. So, so if we can write T1 by T2 as D2 by D1 raised to power 2 by 5. 2 by 5, is it clear? With a negative sign, right? So this can be written as D2 by D1 is 32 raised to power minus 2 by 5. So 32 is nothing but 2 raised to power 5. So this will be 2 raised to power minus 2. That is 1 by 4. So we can say T2 is equals to 4 times T1. Okay, so the final temperature is 4 times the initial temperature. So option answer is 4. Right. Now look at the another question. The PV diagram of a diatomic gas, ideal gas system going under a cyclic process is shown in the figure. The work done during an adiabatic process, CD, we use gamma equals to 1.4. So it's an adiabatic process and we have given volumes and the pressures at both the states. Okay, so we know that work done in an adiabatic process is minus P2 V2 minus P1 V1 upon gamma minus 1, right? So gamma minus 1. So let us put the values. So D state D is nothing but the state 2, right? So here P2 is 200 and V2 is 3 and P1 is state C. One is state C, which is 100 and V1 is 4 divided by gamma minus 1, so it becomes 0.4. So in the numerator we have 600 minus 400, it will be 200, right? And each in the denominator we have 5 by it will be 2 by 5, right? So this is minus 500 joules. So option 1 is the right answer. Right. So now let us see another question. So for an adiabatic expansion of an ideal gas, the fractional change in its pressure is equals to. So basically we have to find delta P by P. And we know that in an adiabatic process, the slope, which is delta P by delta V, is given as minus gamma P by V, right? So if I rearrange the terms, I can say delta P by P is equals to minus gamma delta V by V. So option 1 is the right answer. Okay, so let us see one more question. Which one is the correct option for the two different thermodynamic processes? Okay, right. So if you look at the options, we have given more than one graph may be correct, right? So let us see. So let us use elimination. So in option A, we have given adiabatic process in which the volume is constant. So option A is incorrect because here volume is constant for adiabatic process. In second process, in option B, we have given constant pressure for an isothermal process. So again, it is incorrect. Now in C, so for a we have VT graph is given and for isothermal process the temperature is constant. So this isothermal curve is okay. And if we talk about VT proportionality, let us see. So we know that T V raised to power gamma minus 1 is constant. And this gamma minus 1 is positive, right? So it means if temperature increases, volume will decrease. So this is happening. So we have a non-linear graph. So C option, so this C graph is correct. Now let us see the D graph. So for D, we have for isothermal process, we have a vertical line parallel to the to the pressure axis, and we have a same temperature. So isothermal graph is correct. And for adiabatic process, can you see as the temperature increases, pressure is also increasing. Now let us see the relation. So we know that P raised to power 1 minus gamma, T raised to power gamma is constant for adiabatic process, or we can write it as P raised to power P times T raised to power gamma upon 1 minus gamma. Now 1 minus gamma is negative, so we can say this quantity is negative, right? So we can say P is inversely proportional to T raised to power gamma upon 1 minus gamma, or I can write this as T raised to power gamma upon gamma minus 1. So now this becomes positive, right? So we can say P is proportional to T raised to power some positive constant. So we can say as the temperature increases, pressure should also increase. So that is what happening in this particular graph. So D graph is also correct. So we can say the answer is 2. C and D both are correct. Okay, so now let us see the another question. So 1 mole of a gas at temperature T is adiabatically expanded to double its volume. So the volume is increasing, let us say from V to 2V, and the process is adiabatic. And we have given number of moles as 1. The work done by the gas in the process, and the gamma value is also given, that is 3 by 2. And if you look at the options are in terms of T and R. Okay, and we know that the work done in adiabatic process is minus nR delta T divided by gamma minus 1. So in this formula, we know the value of n and we know the value of gamma minus 1. R is again a constant. So if you are able to find the final temperature, we can find the work done. Now let us see how we can find the final temperature. So we know that Tv raised to power gamma minus 1 is constant. So if that is the case, we can say the initial temperature and times the initial volume raised to power 3 by 2 minus 1 is equals to final temperature times V2 raised to power 3 by 2 minus 1. So T2 is nothing but T1 times V1 by V2 raised to power 1 by 2. And we know that V2 is twice of V1, right? So we will get, and T1 is nothing but T. So it is nothing but 1 by 2 raised to power 1 by 2. So it is T by root 2. So this is the final temperature. So we can write this as minus 1 R T by root 2 minus T divided by 3 by 2 minus 1. So if I take T common in the numerator, so we'll get minus RT as 1 by root 2 minus 1 divided by 1 by 2. Now let us multiply numerator and denominator by 2. So we will get RT root 2 minus 2. So yeah, so root 2 minus 2, and there is a negative in the outside, right? So it becomes 2 minus root 2. So 2 minus root 2 times RT. So option 4 is the right answer. Okay, now let us see this question. So match the list 1 and with the list 2. So in the list 1, we have given different types of processes. In the list 2, we have given different conditions for those processes, right? So let us see. So isothermal process. So in list 2, we have given work done by the gas decreases internal energy. Okay, let us see all the options. No change in the internal energy. So in an isothermal process, delta T is 0. If delta T is 0, there will be no change in the internal energy. So, so we can say A corresponds to second. So if A corresponds to second, we can eliminate option 3 and option 4 because there A corresponds to 1. Now, let us see other examples. So no work is done on or by the system. So if you look at the fourth option in list 2, no work is done on or by the gas. So it means it's an isochoric process. So C corresponds to 4. So C corresponds to 4, A corresponds to T. So again, we can eliminate option 1. So we can find the, so second option is the right answer. So whenever we have such kind of a question, you can always solve such questions by using elimination technique. So option 2 is the right answer. Now let us see another question. 1 mole of an ideal gas is taken through a adiabatic process where the temperature rises from 27 degrees Celsius to 37 degrees Celsius. If the ideal gas is composed of a polyatomic molecule that has 47 vibrational modes, which of the following is true? So we have to find, so okay, right. So in the option we have given work done by the gas and on the gas. So basically we have to find the work done. And increase in temperature is given to us. So we can say delta W will be minus N R delta T. So the increase in temperature is 10, right? 10 degrees Celsius divided by gamma minus 1. So it's a polyatomic molecule that has 4 vibrational modes. So we have translational, rotational, and vibrational. For polyatomic, there are 3 modes of translation, 3 degree of freedom of rotation. And if we have 4 vibrational mode for a given vibrational mode, there are 2 degree of freedom. So 4 multiplied with 2 So we can say the degree of freedom for this polyatomic molecule will be 3 plus 3 plus 8. So it will be 14. So F will be 14. So if F is 14, gamma will be 1 plus 2 by F. So it is 1 plus 2 by 14. So it is nothing but 8 by 7. So it is 8 by 7. Sorry, gamma is 8 by 7 minus 1, right? 8 by 7 minus 1. So basically this is the formula. So this can be written as minus 10 times 8.314 divided by 1 by 7. So if you multiply this with 7, so you can clearly see that it is coming to be close to 580, right? So and it comes out to be negative. So it is minus 582 joules. And since it is negative, it means the work done is on the gas. So it is 582 joules, and work done on the gas is close to 582 joules. So option 2 is the right answer. Let us see one more case. A monatomic ideal gas initially at temperature T1 is enclosed in a cylinder fitted with a piston, frictionless piston, and the gas is allowed to expand adiabatically to a temperature T2 by releasing the piston suddenly. So we have given releasing the piston suddenly, so it means it's a quick process, and it's an adiabatic process. If L1 and L2 are the length of the gas column before and after the expansion, then the value of this ratio T1 to T2. Okay. So what we have given, so there is a cylinder, and let us say the piston initial length of the column is L1, and let us say area of cross section is A. Now this piston has moved, say, up to this mark, and the new column length becomes L2. So initial volume is L1 times the area of cross section, and the final volume is L2 times the area of cross section. And we have to find the ratio of temperature. So what we can do, we can use T V raised to power gamma minus 1, which is constant for adiabatic process. So we can say T1 L1 A raised to power gamma minus 1. And what type of gas is it? It is monatomic gas. So in case of monatomic gas, gamma value is 5 by 3. So gamma minus 1 will become 2 by 3. So L1 times A raised to power 2 by 3. So equals to T2 L2 times A raised to power 2 by 3. So we have to find T1 by T2. So that will be L2 by L1 raised to power 2 by 3. L2 by L1 raised to power 2 by 3. So option 2 is the right answer. Okay, right. So in this question, consider two containers A and B containing monatomic gas at the same pressure, P, V, and T, and same pressure, same volume, and same temperature. So we have given identical container, and initially both have the same pressure, volume, and temperature. So this is container A, this is container B. The gas in A is compressed isothermally to 1/8 of its original volume. So the volume has decreased and becomes 1/8 of its initial volume, and this process is isothermal in container A. In container B, the gas is compressed adiabatically, so from V to V by 8 adiabatically. Right? So the ratio of the final pressures of gas in B to that in gas A. Okay, right. So let us say the final pressure of gas in container B is PB, and the final pressure of gas in container A is PA. So for isothermal process for container A, we can apply it's a isothermal process of P1 V1 is equals to P2 V2. So we can say PV is equals to PA times V by 8. So PA is nothing but 8 times P. Now for container B, we know that PV raised to power gamma is constant, and and what type of gas do we have? So right, so compressed. So let me just check the type of gas we are having. Monatomic gas, sorry. So gas is monatomic. So it will be PV raised to power 5 by 3, because gamma value is 5 by 3 for monatomic gas. Then it becomes pressure becomes PB, and volume will become V by 8 raised to power 5 by 3. Now this V will get eliminated, and PB is nothing but 2 raised to power 3 raised to power 5 by 3 times P. which is nothing but 32 times P. So now we know what is the value of PB. So we have to find the ratio of PB to PA. So 32P divided by 8P, which is nothing but 4. So option 4 is the right answer. Right. So let us see one more case. So here, which of the following is an equivalent cyclic process corresponding to the thermodynamic cycle given in the figure? So we have given a closed cyclic process, and A to B, 1 to 2 is a adiabatic process. And clearly 2 to 3 is a isothermal process, isobaric process, and 3 to 1 is a isochoric process. Now we have to see which of the following VT graphs is correct. Okay, right. So here, whenever we have such kind of a question, we can use elimination. So let us consider one particular process. Let us say 2 to 3, right? Now 2 to 3 is a isobaric process. So if I look at option A, isobaric, right? 2 to 3. So it's a VT graph. If it is isobaric, it will be a straight line, right? So 2 to 3 is a straight line, and again here the volume is decreasing. So in option A, the graph is correct. Similarly, in option C, the graph is correct, 2 to 3. But in B, 2 to 3, in VT graph, it has to be a straight line, but it is a curved line, right? Can you see? So B is incorrect. In C again, 2 to 3 is given as a isochoric. So D is again incorrect. Right. So now we are left with only two options, A and B, A and C. 1 to 2 is a adiabatic process, right? So, but in if you look at option A, 1 to 2 is given a linear graph, right? And we know that in case of adiabatic process, the graph is non-linear. So option A is incorrect. But in C, we have a non-linear graph. So option C is the right answer, right? Now let us see another type of process, which is a polytropic process. Mathematically, it looks similar to a adiabatic process, but in polytropic, delta Q is non-zero, right? It is not equals to 0. And in this, we have PV raised to power A equals to constant, where A is not equals to gamma, right? And for pressure, we can write P raised to power 1 minus A T raised to power A equals to constant, or we can write Pt raised to power A upon 1 minus A is constant, right? Similar to the adiabatic process. And TV raised to power A minus 1 is constant. And again, what we have to do, it is same formula as for the adiabatic, but we have replaced gamma with A. So you do remember this formula, right? So let us see a typical question for this particular section. So we have given a thermodynamic process on a PV diagram for 1 mole of an ideal gas. So N is given. If a volume V2 is 2 times V1, then the ratio of the temperature. So we have given PV raised to power 1 by 2 is constant. So we can say A value, the value of A is 1 by 2. And we have to find the ratio of temperature, and we know the ratio of volume. So what is the relation between temperature and volume? So it is TV raised to power A minus 1 is constant. So if we apply this proportionality, so we can say T1 V1 raised to power A minus 1. So A minus 1 is 1 by 2 minus 1, right? That is minus 1 by 2. This is A minus 1. So minus 1 by 2 is equals to T2 V2 raised to power minus 1 by 2. So T2 by T1 is equals to V1 by V2 raised to power minus 1 by 2. And V1 by V2 is nothing but 1 by 2, right? 1 by 2 raised to power minus 1 by 2. And this can be written as 2 raised to power 1 by 2, which is root 2. So option 3 is the right answer. Okay, now let us see another question. In certain thermodynamic process, the pressure of a gas depends on its volume. So pressure is given as some constant times V raised to power 3. The work done when the temperature changes from 100 to 300 degrees Celsius will be equals to some constant times nr, where n is denotes the number of moles of the gas. So we have to find that constant. So basically we have to find the work done. So work done will be given by minus nr delta t upon a minus 1. And if you look at this, we can rewrite this as PV raised to power minus 3 equals to some constant. So we can say this value is nothing but A. So A is equals to 3. So minus nr, and the increase in temperature is 200, and minus 3 minus 1 because A is minus 3. So minus 4, so this will be 50. So it will become nr times 50. So if I want to fill this blank, it will be 50. Okay, now let us see the another question. The volume V of 1 mole of monatomic gas. So N is given as 1, and we have given monatomic gas. So we can say F is 3, or gamma, right? F is 3. And changes with temperature T. Volume is changing with temperature T according to the relation V is some constant times T raised to power 2 by 3. The work done when the temperature changes by 90 Kelvin will be XR. The value of X will be, okay. So we can write it as T will be directly proportional to V raised to power 3 by 2, or I can write this as T V raised to power minus 3 by 2. So this is constant, right? And we know that in case of a polytropic process, TV raised to power A minus 1 is constant. So if I compare these two results, so we can say A minus 1 is equals to minus 3 by 2. So A is equals to 1 minus 3 by 2. So it comes out to be minus 1 by 2. So A is minus 1 by 2. And we have to find the work done. So work done will be minus nRT delta T divided by A minus 1. So minus nR delta T here is given as 90 Kelvin. A is given as minus 1 by 2. So minus, so in the denominator, n value is given as 1. So 1 times R times 90 divided by minus 3 by 2. So this negative will get cancelled out. So we have, and this 3 will give us 30 in the numerator. So it is 60 R. So we can say the X value will be 60. Right. So let us see one more question. So n moles of an ideal gas undergoes the process A to B as shown in the figure. The maximum temperature of the gas during the process will be, right. So basically we have to find the maximum temperature as the gas as we are going from A to B. So what we can do here. So first of all, let us see what type of process it is. So we can say, we can draw the equation of this line, and it can be written as, it's a straight line. So we can use point slope formula. So we can say the slope is nothing but minus of 2 P naught minus P naught on 2 V naught minus V naught, right? So this is nothing but minus P naught by V naught. So, so we can write P minus. So if I consider point A, so its coordinates are V naught comma 2 P naught. So it will be P minus 2 P naught equals to slope P naught by V naught times V minus V naught, right? So if we simplify this, so pressure will be 2 P naught minus P naught by V naught times V plus P naught. So it is nothing but minus P naught by V naught times V plus 3 P naught. So basically we have pressure as a function of volume, and we want to find the temperature. Now if I write temperature as a function of volume, then we can use maxima minima, and we can find the maximum value of the temperature. So by ideal gas equation, temperature is PV upon nR. So we can say V upon nR times minus P naught by V naught times V plus 3 P naught. So this is nothing but the temperature. So we can write this as minus P naught by nR. Okay, right. Keep let us keep nR outside, right? So we can write this as 1 by nR times minus P naught by V naught times V square plus 3 P naught V. Now it's a quadratic function, right? So if I want to find the maximum value of the temperature, so let us differentiate this. So dt by dV is equals to 1 by nR. It will become minus 2 P naught by V naught times V plus 3 P naught. Now, what we can do, we can put this equals to 0. So dt by dv will be equals to 0 for the maxima or minimum value. So if I put it equals to 0, minus 2 p naught by v naught times v plus 3 v naught will be 0. So from here, v comes out to be plus 3 v naught by 2. So we can see that when the volume is 1.5 v naught, at that instant, at that particular volume, the temperature will be maximum. So maximum temperature will be, now let us put the value of v as 3 v naught by 2 in the temperature formula. So it will be 1 by nr minus p naught by v naught, and this will become 9 by 4 v naught square plus 3 p naught v naught by 2 times 3. So 1 v naught will get cancelled out from the first term. So we have 9 by 2 minus 9 by 4 in the bracket. So it is nothing but 9 by 4, right? 9 by 4 p naught v naught upon nr. So that is the maximum value of the temperature. 9 times p naught v naught upon 4 nr. So option C is the right answer. Okay, right. So the next process is cyclic process. So what is the cyclic process? So in cyclic process, we again come back to the same initial state. And in cyclic process, delta U is 0. And if I want to find the work done, it will be this shaded area. Okay, so the area enclosed by the cycle. Now, if we have a clockwise cycle, the work done will be positive. And if we have a counterclockwise cycle, the work done will be negative. For in this particular diagram, since we have a counterclockwise cycle, the work done will be negative.
Now let us see the question based on the cyclic process. A real gas within a closed chamber at 27 degrees Celsius undergoes a cyclic process. The gas obeys PV raised to power 3 equals to RT equation for the path A to B. The net work done in the complete cycle is, so from C to A the work done will be 0, right? If we are able to find the work done from A to B and work done from B to C and add those two work dones, we'll get the total work done in the cyclic process, right? Since this AB is curved, we cannot find the work done with the graph. What we can do, so here we have given P as a function of V, right? And we have given that the gas is contained at a temperature 27 degrees Celsius. So what we're going to do, we know that there is a general formula for work done. So if I want to find the work done from A to B, so what we're going to do, so work done is given as dW can be given as PdV. Now what I'm going to do, I will substitute P in terms of temperature and volume. So this can be written as RT upon V cube times dV. And then what we can do, we can integrate this and we know what is the change in volume. So volume is changing from 2 to 4 meter cube. So from 2 to 4, we can solve this integration. So work done from A to B will be given as RT, and then the integration of 1 by V square, which is nothing but minus 1 by 2V square, right? Because we can take V in the numerator, so V raised to the minus 3, and then we have in the integration will be V raised to the minus 3 plus 1 upon minus 3 plus 1. And the limit is from 2 to 4. Now let us substitute the value. We have to take R as 8. Temperature is given as 27 degrees Celsius, so that will be 300 Kelvin times 2. We can take 2 out, and it will be 1 by 2 square minus 1 by 4 square. So this comes out to be, this will be 4, so 1200 times 1 by 4 minus 1 by 16. So it will be 1200 times 3 divided by 16, and it will be 4, 300, and this comes out to be 75. So 75 times 3 is 225 joules. So work done from A to B is 225 joules. Now it is easy to find the work done from B to C because it's an isobaric process, and in case of isobaric process the work done will be P delta V. So work done from B to C will be pressure is 10 Newton per meter square, and final volume is 2, initial volume is 4. So that will be minus 20 joules. So the total work done in this cyclic process will be 225 minus 20, so that comes out to be 205 joules. So option 2 is the right answer. Now let us see the work done in this cyclic process. So the heat absorbed by the system in going through the given cyclic process. So we have to find the heat absorbed. Now in a cyclic process, delta U is 0. So delta Q is nothing but the work done by the gas. Since it's a clockwise cycle, the work done will be positive, so delta Q is also positive. It means the heat is being absorbed by the system. Now if you look at this, it looks like a circle, but actually we can say it's kind of an ellipse, and we can say the semi-major axis is that much, and this will be the semi-minor axis. This is A and this is B. So A is nothing but 340 minus 60 by 2. So 340 minus 60 by 2 times 10 raised to power 3, because it is given in kilopascal. And B is 340 minus 60 by 2 cc, and in 1 cc we have 10 raised to power minus 6 meter cube. This will be meter cube and this will be pascal. Now if you simplify this, this will be 340 minus 60, that will be 280 by 2 times 10 raised to power 3 pascals, which is 140, or you can say 14 into 10 raised to power 4 pascals, and this will be 140 into 10 raised to power minus 6 meter cube. Now what is the work done? That will be pi AB. So 3.14. A is pi AB is the area of an ellipse. A is 14 into 10 raised to power 4, and B is 14 into 10 raised to power minus 5. So this will be 196, or you can say 19.6 times 3.14. So 19 times 3, so it will be close to 60, right? So option 2 is the right answer. Now let us see the question based on the concept when the density of the gas is constant, and here we have to use this relation that P m naught is equals to rho RT, where m naught is the molar mass of the gas, right? P is the pressure, T is the temperature, and rho is the density, and R is the gas constant. So here P can be written as rho R by m naught times T, and we have given that it's a straight line, and we have given 3 densities. So PT diagram of ideal gas having 3 different densities, rho 1, rho 2, and rho 3, in 3 different cases is shown where of the which of the following is correct. So here you have to assume that all these graphs are passing through the origin, right? That is the assumption. And if you look at the relation between pressure and temperature, we can say the slope is, for a given gas, the slope is directly proportional to the density. So the greater the density, greater the slope. So it means for this graph the slope is maximum. We can say rho 1 is greater than rho 2 is greater than rho 3. So if you look at the option 1 is the right answer.
Next concept is second law of thermodynamics. So in this law, we'll study 2 statements, and those statements will form the basis for heat engine and the refrigeration cycle. So let us see. So the first statement is Kelvin-Planck statement. According to this statement, no process is possible whose sole result is the absorption of heat from a reservoir and the complete conversion of heat into work. So what does it mean? Let us take an example of a steam engine. So in steam engine, we have coal, and that coal will give energy to water, and then water then converted into steam. Now that steam will do work on the impeller, and the energy is being produced, and then the steam will get condensed and it passes through the heat exchanger, and the heat is being released to the surrounding. So whatever energy that we have given to the water, that entire energy is not converted completely into work done. So there has been some losses, some heat is being released to the surrounding. So that is the basis of heat engine. Now the second statement is Clause's statement, which states that no process is possible whose sole result is transfer of heat from a colder object to a hotter object. We all know heat always flow from a high temperature to a low temperature, but if suppose if I want to remove heat from a colder body to a hotter body, we have to do some work. And this is basically the example of a refrigeration cycle. So what happens in refrigeration cycle? We have to do some work in the form, we have to provide some energy to the compressor, which will do work on the refrigerant. And in that, it will be able to extract heat from a colder object and will pump heat to a hotter object, that is the surrounding. So let us study heat engine and the refrigerators. So in heat engine, it's a thermodynamic system and is made to undergo a cyclic process which results in a conversion of heat into work. So let us see the basic structure. So we have a thermodynamic system and there is a hot reservoir and there is a cold reservoir. We can also call a hot reservoir as source. And let us say the temperature of the hot reservoir is T1 and the temperature of cold reservoir is T2. We can also call cold reservoir as sink. Now, in heat engine, the heat is being taken from the hot reservoir and some of the heat will be rejected to the sink, and in doing that there will be some work done by the thermodynamic system, right? So if we apply energy conservation, so can you see Q1 is entering the system, Q2 and W are going out of the system. So by energy conservation we can say Q1 is equals to Q2 plus W, and W will be nothing but Q1 minus Q2. So if I want to find the efficiency of a heat engine, it is defined as the work done per unit heat supplied, right? Heat supplied. So it will be W upon Q1, where Q1 is the heat supplied to the system. So Q1 minus Q2 upon Q, and can be also written as 1 minus Q2 by Q1. So this formula you have to remember in case of a heat engine. Now let us see a typical question from heat engine. So helium gas goes through a cyclic process ABCDA consisting of two isochoric and isobaric lines as shown in the figure. The efficiency of this cycle is nearly. So basically we have to find the efficiency, and we know that efficiency is work divided by the heat supplied, right? Now in this cycle there are four processes. So from A to B there is a isochoric, it is an isochoric process, right? So in this process the pressure is increasing. So suppose if I want to find whether the heat is being supplied to the system or is the heat is being extracted from the system, let us figure out. So we know that it's an isochoric process, so delta Q will be N CV delta T, right? Now what is okay, right? So CV can be written as F by 2R delta T, right? So NR delta T by ideal gas equation, it can be written as F by 2. It will be V naught times 2 P naught minus P naught. Can you see? It comes out to be a positive, so it is greater than 0, right? So in the process A to B, the heat is being supplied to the system. Now let us see the process B to C, which is a isobaric process. Again, in this process, the pressure is constant, but the volume is increasing. So we can say the heat is being supplied to the system. So it will be NCP delta T. So which is nothing but F by 2 plus 1 NR delta T. And this can be written as F by 2 plus 1. And NR delta T can be written as 2P naught times final volume minus initial volume, which is again positive. But if you consider process C to D, C to D is again isochoric process. But in this case, the pressure is decreasing. So here the delta Q will be negative. Similarly, from D to A, it is isobaric. Here again, the volume is decreasing for the same pressure. So again, delta Q will be negative. So if we want to, what heats we have to use? So we have to use only those processes in which heat is supplied to the system. So in this case, I can say, let us say this is delta Q1 and this is delta Q2. So it will be, in the denominator will be having F by 2 V naught times P naught plus F by 2 plus 1 2 P naught times V naught, right? And what is the work done? Since it's a cyclic process and we have a clockwise cycle, the area enclosed by the cycle will be the work done, and which is nothing but this base is V naught and the height is P naught. So work done will be P naught V naught. So let us, and we have given a helium gas, which is a monatomic gas. So degree of freedom will be 3. So let us plug in the values. So we have P naught V naught divided by 3 by 2 plus 3 by 2 plus 1 times 2. And this P naught V naught will be common. So this will get cancelled out. So it will become 1 upon 3 by 2 plus 3 plus 2, right? and this can be written as 2 divided by 3 plus it will be 5 plus 2 10, so it will be 2 by 13. Okay, so we have to find the percentage efficiency. So percentage efficiency is nothing but 100 times 2 by 13, so it is nothing but 200 by 13, and which will be close to 15.4%. So option A is the right answer. Now let us see one more example. So we have given a heat engine is involved with the exchange of heat of 1915 joules, minus 40 joules, 125 joules, and minus q joules. During one cycle, achieving an efficiency of 50%, the value of q. Okay, so we know that efficiency, percentage efficiency, is nothing but work done upon heat supplied. And in this heat supplied, we have to consider only those processes where heat is being supplied to the system. Now, we can clearly see that for this particular, for the denominator, we have to use plus 1915 plus 125 because other two heats are negative. So those are being rejected from the system. Now, what is the work done? And we know that if we apply energy conservation, the work done will be total heat exchange, right? So that we have seen in heat engine, it is Q1 minus Q2, right? So total heat exchange. So that will be 1915 plus 125 minus 40 minus Q. So this will become 2040 minus 40 minus Q. And this is the work done, right? So let us put this value in this formula. So we will get 2000 minus Q divided by 2040. And the efficiency is 50%, right? So this is 50%. So we can say 50 by 100. So it will be 1 by 2 equals to 2000 minus Q divided by 2040. So this will give us 1020. So Q will be 2000 minus 1020. So it comes out to be 980 joules. So option C is the right answer. Okay, right. So now let us see your refrigerators and heat pumps. So in refrigerator, if you want to cool a chamber and the surrounding is at a high temperature, we'll call it a refrigerator. So let us see. Again, we have a hot reservoir and a cold reservoir. Hot reservoir is at temperature T1, cold reservoir is at temperature T2. Now in this case, we are taking heat from a cold reservoir and pumping heat to a hot reservoir. And in doing that, we have to do some work. Now in case of a refrigerator, this cold reservoir is the area of concern, right? We want to maximize this Q2, right? So we want to maximize this Q2. So first of all, if I apply energy conservation for this system, we can clearly see that work done will be Q minus Q1 minus Q2. And in refrigerator, we'll talk about a new quantity, which is coefficient of performance. So what is the coefficient of performance? So we want to maximize Q2 per unit work done, right? So coefficient of performance in case of a refrigerator will be Q2 by W, where Q2 is the heat removed from the cold reservoir and W is the work done on the system. So you have to remember this formula. Coefficient performance, greater the value of coefficient performance, more efficient the refrigerator is. Now, what is a heat pump? So in heat pump, the cycle will be same, but if you want to heat up a chamber and the surrounding at a lower temperature, so in this case, the area of concern will be the hot reservoir. Let me give you an idea. Suppose you are in a colder region and your room is quite cozy. It has a high temperature as compared to the surrounding outside the snow. So in that case, I want to keep the temperature of that room high. So for that, we have to continuously pump heat to that room, right? So that is the cycle for that particular process for the heat pumps. So in this case, hot reservoir is the area of concern and we want to maximize this Q1. So in this case, we can say the coefficient of performance for heat pump will be Q1 divided by work done, right? Work done on the system. So do remember these formulas. Now let us see what are reversible processes and what are irreversible processes. So reversible processes are those processes that can be reversed in order to obtain the initial state of the system. So we can easily get back to the original state of the system. But the irreversible processes will be completely opposite of this, which cannot be reversed. For example, the explosion of the bomb is an irreversible process, right? Now, what causes irreversibility? So there are a few causes. First is that there are some processes which take the system to non-equilibrium states. So it will increase irreversibility, and there will be some losses while some process is going on. So there will be some dissipative effects, some friction will be there, some viscous forces will be there. So we can say it adds up to irreversibility. But how we can attain reversibility? So there are some ways. First, we can make process very slow. So we call those processes as quasi static process, make them very slow. And second thing, we can try to remove dissipative effects as far as possible. So if we are able to achieve these two conditions, we can make a process reversible. Now, by using reversible process, we can have an engine which utilize only reversible processes and will get the maximum efficiency out of it. Now let us say, so Carnot engine is an ideal engine based on a reversible cycle of 4 operations in succession. So there will be 4 operations. Let us say, first, let us say on the y-axis we have pressure, on the x-axis we have volume. So first process is isothermal expansion. It is from A to B. So it is in this direction, isothermal expansion. Then the second process is adiabatic expansion. It is from B to C. And the third process is isothermal compression. It is from C to D. And the fourth process is adiabatic compression. It is from D to A. Right? So this is basically the Carnot engine. And do remember, in Carnot engine, the heat is being supplied to the system in this isothermal expansion. So we can say Q1 heat is being supplied and Q2 heat is being rejected in the second isothermal compression process, right? So in case of a Carnot engine, Q1 by Q2 is equals to T1 by T2, where T1 is the temperature of hot reservoir and T2 is the temperature of cold reservoir. And similarly, we can do the necessary modification in the efficiency formula. So Q2 by Q1 can be replaced with T2 by T1. So you have to remember these two formulas. Though Carnot engine is not in the syllabus, but usually if we have a question on heat engine and the refrigeration cycle, it uses the concept of Carnot. Only in that case, they will be able to form some good questions.
Now let us say this question, it is based on the Carnot engine, though it is not in the syllabus, but actually this problem is based on the Carnot engine. So two different adiabatic paths for the same gas intersect two isothermal curves. So these two curves are isothermal. So we can say on these two curves, let us say here the temperature is T1. On this isotherm, the temperature is T2, right? And these two are adiabatic process. Okay. Now the ratio between the relation between the ratio VA by VD and the ratio VB by VC. So VA is the volume at state A, VB is the VD is the volume at state D, and VB is the volume at state B, and VC is the volume at state C. So what we can do, if we consider the process from D to A, it's a adiabatic curve. So we can say T2 times volume at D raised to power gamma minus 1 should be equals to T1 times VA raised to power gamma minus 1, right? Now if we consider adiabatic process B to C, it will be T1 times VB raised to power gamma minus 1. It will be equals to T2 times VC raised to power gamma minus 1. Now if you compare or if you divide these two equations, we will get VD by VB is equals to VA by VC, right? So we can say VA by VD is equals to VC by VB by rearranging by rearranging the terms, right? I have taken VD on the other side, VC on the other side. So if you look at the option, then option 2 is the right answer.
A Carnot engine having an efficiency of 1 by 10 is being used as a refrigerator. So we know that efficiency will be 1 minus, it will be Q2 by Q1, right? And it is given as 1 by 10. If work done on the refrigerator is 10 joules, so we know that Q1 minus Q2 is work done, which is 10. then the amount of heat absorbed from the reservoir at lower temperature. So at lower temperature, basically we have to find Q2, right? So we have to find Q2. So Q2 is equals to Q1 minus 10 from this equation. And from the first equation, from here, we can say Q2 by Q1 is equals to 9 by 10. So we can write Q1 as 10 by 9 times Q2. So let us substitute this value in this equation. So Q2 is equals to 10 by 9 Q2 minus 10. So we can say 10 by 9 minus 1 times Q2 is equals to 10. So Q2 comes out to be 90 joules. So option D is the right answer. Now let us see one more example. So two ideal Carnot engines operates in cascade. All heat given up by one engine is used by the other engine to produce work between temperature T1 and T2. The temperature of the hot reservoir of the first engine is T1 and the temperature of the cold reservoir of the second engine is T2, and T is the temperature of the sink of the first engine, which is also the source of the second engine. Basically, what do we have? So let me draw the diagram. So here we have given a reservoir which is at temperature T1, and there is another reservoir which is at temperature T, and there is another reservoir which is at temperature T2. Now here we have one engine, and this is the another engine. Now we are so heat is being extracted from this reservoir. That is, this heat is Q1, and it releases heat Q to T, right? And then the second engine takes heat from T, the same heat, right? And it releases Q2 heat to the this reservoir, right? So in doing that, the first engine does the work, say W, and the second engine also do the same work, W. Now we have to find the temperature of this third reservoir, which is in the middle. And how is T is related to T1 and T2? Both the engines perform equal amount of work, right? So we know that um, as per the definition of Carnot engine, Q1 by Q for the first engine will be T1 by T. And we can also say T by T2 for the second engine will be Q by Q2, right? So so this way we can write. Now, if we talk about the work done, so work done of the first engine will be Q1 minus Q. And similarly, the work done for the second engine will be Q minus Q2, right? So basically, we want to find the relation between T1, T2, and T. So what we're going to do, we'll try to eliminate Q1, Q2, and Q, right? So what we're going to do, we will, so from this equation, we can say 2Q is equals to Q1 plus Q2. Now I can write Q1 in terms of Q, right? So Q1 will be capital Q times T1 by T, and Q2 can be written as T2 by T times Q. Oh, I think this is not visible to us. Let me write this thing on the left hand side. So I can say 2Q is equals to Q1 plus Q2, and Q1 can be written as T1 by T times Q, and Q2 can be written as T2 by T times Q. So can you see this capital Q will get eliminated, and we can say T is nothing but T1 plus T2 by 2. So do remember, it will be the mean of the two temperatures. So the option B is the right answer. Now this is the last concept of this one shot, which is entropy. Now according to second law of thermodynamics, for a reversible process, the heat supplied is nothing but T times ds, where dq is heat supplied, T is the temperature, and ds is the change in entropy. So by using this relation, we can find the heat supplied by taking the integration of TDS. So how we can use this? If a graph is given to us, suppose we have given, say on the y-axis we have temperature, on the x-axis we have entropy, and suppose there is a graph from A to B. Now, if I want to find the area under this graph, let us say this is the area. Now this area is nothing but integral TDS, right? It is area under temperature and entropy graph. So do remember this. Let us see a question based on this concept. The temperature entropy diagram of a reversible engine cycle is given in the figure. Its efficiency is, so we know that efficiency is nothing but work done upon heat supplied, right? And only those processes in which heat is being given to the system. Now, let me call this as A, this process A to B, then B to C, and C to A. C to A. There are three processes. Now, in the process A to B, can we find the area under the graph? Yes, it can. We can easily find that. So, can you see this trapezium? So we can say delta Q from A to B will be area under the temperature entropy graph. So it will be half sum of parallel sides, which will be 2 T naught plus T naught, and then the distance between parallel side, which is nothing but 2 S naught minus S naught. So this comes out to be 1.5 T naught S naught. Now for the process A to B, B to C. In the process B to C, can you see the entropy is decreasing? So we can say it is the heat rejected from the system. So delta Q B to C. So it will be half, not half. It is a so if you look at this, it is a rectangle, right? This area. So it will be S naught times T naught. Okay, so I can say in this case Q1 is nothing but 1.5 T naught S naught, and Q2 is S naught T naught, and work done is given as Q1 minus Q2. Because if you look at the process CA, in process CA, the area under the graph will be 0. C2A, it is 0, right? Area under the graph is 0. Now, because here ds is 0. Now, I want to find the work done. So Q1 minus Q2, so that will be 1.5 minus 1 times S naught T naught. Okay, now let us put the value. So 0.5 S naught T naught divided by heat supplied, that is Q1, right? So 1.5 S naught T naught. So which comes out to be 1 by 3. So option D is the right answer. So I hope whatever concept we have discussed in the video are clear to you, and definitely you will get a question from these concepts only in the exam.
If you find videos of this series useful, so it is highly recommended for you to join PracBee's revision program. So in this program, we're going to cover 10 blocks in 10 weeks, and we'll give you a target of 1 chapter per day, and we'll be able to cover all relevant chapters by the first attempt of JEE Mains. And how you can join this revision program? By clicking on the link given in the description. And one more thing you can do, please drop a comment. Let us know what else we can do for you to make this series better. Thank you.